Hello, everyone. Let's continue our optimization process. Now, the idea is that what do we do if the interval is not closed? So, in our examples, not closed mean that the endpoints are not going to be necessarily included. So, it could be from A open to B closed, or you could have like from A closed to infinity. So, one of the two endpoints, at least one of the two endpoints, will be an open endpoint. And of course, the idea, this is very similar to what we've done for so long now. How do you check how something behaves around an open endpoint? You define and you compute the corresponding limit. Anyway, so to see the general idea, I will start first by looking over some examples of function defined over non-closed interval and see how we can find global maximums and global minimums. So for my first example, I have a function that is defined between A and B. So A is closed and B is open. So when I look at this graph in blue here and I look for the lowest possible value, I can see it. It's going to happen at the first critical point here, C1, where f prime is 0. So the smallest possible value is reached when x is equal to C1. So here, this is the lowest possible value. Then if we move the next, so between critical points and endpoints, the next one would be f of C3. So here, f of C3 would be the next one. I'm just comparing numerically the y value here. So poof, so poof, f of C3. And then it would be at the beginning at A. So f of A would be the next one to in line. So I'm just looking at them in ascending order. So, and then f of C2 would be the next one. So, but then if I'm trying to get to the highest possible value, as I'm getting closer to B, this function is going up. However, it's getting closer to a vertical asymptote. It's going to infinity. So what's happening at B here? Well, B is an open endpoint. So what we can do here is to study its behavior at this open endpoint is to set up a limit as x approaches to B. So as x approaches to B, from the left side, we see that this limit goes to infinity. So it's the biggest thing out there. So here, everything that we've computed will be smaller than this limit as x approaches b minus of f of x because it's going up to infinity. So when you look at this graph here, it has a global minimum at the beginning at f of c1, but it does not have a global maximum because the biggest value that you get here is reached with a limit. So here, the only way you can go to infinity is with a limit. There's no highest possible values. There's no highest global maximum within A and B. So here, there's no global maximum, just a global minimum. Now for the next example, if I look at the lowest possible value, actually here, so my function is first is defined between A and B, open at A, close at B. Well, the first value, the lowest part of this graph is actually at A, but at A we have a hole. And the only way you can reach a hole here is by computing the limit as x approaches A from the right. So here, from the right, I can reach that hole by setting up a limit. And that's the lowest possible part of that graph. But there's no x value that will reach that hole. You can only get there by computing a limit. So the limit is the lowest possible thing here. And then in this chain of y values, the next one would be the endpoint b here. So b, so at b, my function is somewhere in the middle here. And then the highest possible value is at the critical point. So f of c1 will give you the highest possible output. So we have a global maximum for that function at C1 at a critical point. But we don't have a global minimum because the lowest possible thing that we can go to on this graph is to a hole, but hole is not something, so it's an open endpoint. So here I really want to stress the fact that this open endpoint at A is a limit that you can set up and compute. So as soon as you see an open endpoint, you need to click there's a limit to define/compute, and then you just compare. You compare the value of your limit or your limits if you have more than one, the close endpoints and the critical points. And if, like in the second example, the lowest possible value is reached at a limit, then there's no global minimum. But the highest possible value was reached at a critical point, so we got a global maximum. All right, so for the next example, I have a function defined from a, including a, to infinity. Again, to infinity, that's an open endpoint. We know there's a limit to set up and define that we're going to use. So here, the highest possible value for your graph is reached, let's go from high to low here, is reached at the beginning when x is equal to a. So a is going to be the global maximum. So f of a is the biggest value here, the biggest value for this function. Then it's followed by f at C2, so the second critical point here is my second lowest value, and then f of C1, followed by f of C1 very closely. But then the function will continue to go down and get closer and closer to this horizontal asymptote, and the only way to get there is by computing the limit as f goes to infinity of f of x. So the lowest possible thingy here is a limit, so there's no global minimum, and the global maximum was reached at a closed endpoint. So the closed endpoint are still important. They can still win as the biggest or the smallest value. So very, very crucial thing to remember is that when the limit wins as being the smallest or the biggest thing around, then there's no global minimum or global maximum, depending on what's going on. But it's not always that there's one missing. The last example has two open endpoints. So there's an open endpoint. Oh, just to go back, like, of course, the open endpoint to infinity, for example, C was corresponding to the limit going to infinity. Anyway, so now for the example C here, there's two open endpoints to infinity and minus infinity. So there's two limits to set up and compute. So what is the smallest possible value here? Where the smallest possible value is at the first critical point here at C1. Then there's this horizontal asymptote by the limit here. So the limit going to infinity is the second biggest thingy here. So we have, this is in second position. So that's corresponding, of course, to my second important limit to set up and compute. And then the third thing, so after that first horizontal asymptote to infinity, then the one going to minus infinity is a bit higher up. So this is my second limit. So this second limit is, of course, given by the first open endpoint. So make sure you see the connection between those limits that I have here in my little comparison thing. And then the biggest possible value is reached at the second critical point. So here there is a global min and there is a global max, and they are reached at the critical points for your function. So here, the global minimum, let me just write it down. So the global minimum is reached at the first critical point. So I have M here. Oops, okay, wait. So C1 is my global minimum, and the global maximum is reached at C2. So all this just to say that when you have like non-closed intervals, so you have open endpoints, you have to set up a limit and compute those limits, and then you do the same thing. You compare the value of those limits with the outputs at critical points within the interval and the outputs at endpoints, if there's any closed endpoints. And then if the lowest thing is reached by a limit, if it's only reached by a limit, then there's no global minimums. If the biggest value is only reached by a limit, then there's no global maximum. But if the highest or the lowest thing is reached by something within, so critical points within or a closed endpoint, then there is a global min or a global max. So just going over the method quickly now. So for optimization of continuous function over any interval, to compute global maximums and global minimums of continuous function over that interval, first, just like usual, you compute critical points, which means you compute the derivative and you keep the critical points within the interval that is always specified in the question. Then you compute the y values at any closed endpoints, if any, and at critical points, just like before. And so if you have any open endpoints, you need to compute limits at those open endpoints. So you need to define them and compute them. And then you compare the outputs of the limits to find the global maximum, and you compare the outputs and the limits, the value of the limits, to find the global maximums and the global minimums. And again, if the highest value is only reached at one of those limits, then there's no global maximum. If the lowest value is only reached at one of those limits, then there's no global minimum. All right, let's do an example of optimization of a function over a general interval. So here we go. Let's optimize f of x, which is x times e to the power of minus 0.25x. This is actually a function that we studied before in an example of optimization over a closed interval, but we're going to study it again over the interval 1 to infinity and also over the interval 0 to infinity. So here it's actually two questions, but I just wanted to do examples where we would focus on what happens if you change the interval. Normally, an optimization question is one function and one interval. But for the sake of learning it, I just use the same function over different intervals just to practice. So first, you compute f prime. This is just like before. You need to do a chain rule. So when you do your your product rule, you get the derivative of x times e to the power of minus 0.25x. So you get 1 times e to the power of minus 0.25x plus x times derivative of e to the power of 0.25x, which is e to the power of 0 minus 0.25x times minus 0.25. So if you factor the e, this is just like before. If you factor the e out, you're going to leave behind 1 minus 0.25x. If you're looking for critical points, the only way you can have critical points here is when f prime is equal to 0, because this function never crashes, and this will only happen if x is equal to 4. All right, so I have my critical point 4. So let's do the work for the first interval, so between 1 to infinity. So here I'm starting at 1. It's a close endpoint, so I will evaluate my function at 1. Then I have my critical point 4, which is within the interval from 1 to infinity. But now how do we deal with that infinite? So here that open endpoint induces a limit. And that limit is, of course, going to be set up right here. So here I'm going to compute on the side. So in the table, the way I'm going to write it down, I'm just going to write x goes to infinity, and I'll put the value in the f of x column. So since here the goal is just to study the optimization part, if you do the limit, this is actually an hospital rule question. So as an exercise, you can verify that the limit of this function as x goes to infinity will give you a 0. So it's going to give you 0. So because it's giving you 0 in the table, so you know that the limit is 0, when you're going to compare stuff, so what is the lowest possible value? Well, the lowest possible value is the 0, which is only reached by the limit, and the biggest possible value is given by 1.47, so this is reached at 4. So when you make your conclusion, so here the conclusion is as follow. Because the max is within, so at 4, so there's a global max at x equals 4, but because the lowest value is reached at a limit, there's no global minimum. Okay, so because the lowest possible value is reached within at a limit only, the 0, the lowest value of the y values here is you only get there by a limit, so there's no global minimum. All right, so again here, this is another example, but within the same, just to practice. So let's do from 0 to infinity. Of course, here it's the same open endpoint. Okay, so at infinity, but now we're starting at 0. So if you start at 0, so if you start at 0, the output is 0, and then at 4, it's 1.47, and then you have your limit. It's the same one here. So when you look at your limit, as x goes to infinity. It's the same limit. You're still going to get 0. But now what's interesting is that when you're looking for the smallest values, you find two of them. You find one at 0 and you find one at going to infinity. And of course, your max is still at 1.47, so at 4. So here, one of the minimum is at 0, but we have another, and that 0 is within. And the global max, there's only one. So here, the conclusion is that we have a global maximum. And the global maximum is at x equals 4. And there is also a global minimum. Of course, even if the limit is getting there, and you cannot consider that 1, because 0 gets there too, and because 0 is within, there's a global minimum, in this case, at 0. So make sure these two intervals were chosen for a specific reason. Like I like that second example where we get 2 zeros. A lot of people think, oh, the limit got there, so there's no global minimum. Well, you cannot get there with the limit. But if you get there somewhere else within, then you're good to go. All right, for that example, that's it. All right, next example. We want to optimize x ln of 0.5x plus 1 over the following intervals. Again, this is 3 questions in one. Normally, it's just one function in one interval. But we just want to focus on the new part of the question here, which is dealing with the interval. The first one is the interval from 0 to 1, excluding 0, including 1. And then we'll do excluding 0 to 2 included, and then excluding 0 to infinity. So the first thing you always do is you compute the derivative. So for f prime, this is a product rule. The derivative of x is 1 times the second function plus the first function times the derivative of the second one, which is 1 over 0.5 x times the inside derivative, which is 0.5, and this simplifies to ln of 0.5x, and the 0.5 over 0.5. I forgot to say that the plus 1 goes to 0, and then you're just going to get plus 1. So ln of 0.5x plus 1 is the first derivative, so now we're looking for critical points. Ln of 0.5x plus 1 will crash if x is 0 or strictly negative, but we don't care because we're over the interval 0, 1. So if there's any interesting critical points for us, it will be between 0 and 1 by setting the derivative equal to 0. So here there's a little bit of algebra to do. So we have ln of 0.5x plus 1 equal to 0. We need to solve for x, so we bring the plus 1 on the other side. So we get ln of 0.5x is equal to minus 1. So I just brought the 1 on the right side as a minus 1. Then I just exponentiate on both sides. So you get 0.5x is equal to e to the minus 1. And then you just multiply by 2. So x is equal to 2 times e to the power minus 1. And this is very close to 0.74. So poof, that's your critical point. And of course, when you are computing that critical point, you want to make sure that it's within the interval. But here for all 3 examples, 0.74 will be within the interval that is of interest for us. Again, here, 3 questions in one. So for the first interval, so we're between 0 and 1, but 0 is open. So right away, the reflex is the following. Because 0 is an open endpoint, you need to define a limit. So what I've done for you, I just wrote down the limit. So we need to define the limit as x approaches 0 plus of x ln of 0.5x plus 1. This one can be done by using hospital rule here. So as an exercise, okay, so I'm not going to do it, but as an exercise, you can do it. So if you do compute the limit as x approaches 0 of x ln of 0.5x, you can double check that this is going to give you 1. Okay, so the limit is 1 because the x ln of 0.5x part, which is where the problem lives, goes to 0. So double check it by using by using the good old hospital rule. Okay, so as an exercise. But anyways, the point now is how are you going to use this? Okay, so we're good with limits now. So how are you going to use this limit within your table? So what do we do? How do we set up the table correctly in order to, qu'est-ce qui se passe? Sorry. So I have to set up my table. So here we go. So how do I fill up this table? So first, at 0, on the right side of 0, I have a limit. So you write down the limit that you're going to include here at the beginning. So the limit as x approaches 0 plus, and we just verify that this is giving us a nice 1. Then my critical point at 0.74, if you compute the output at 0.74, you're going to get 0.26. And then we have 1, a closed endpoint, and if you compute the output there, you're going to get 0.31. So now if you compare stuff to make a conclusion, where is the highest possible value? Well, the highest possible value in this table is right here because of that 1. So we have a max here, but it's reached by a limit only. And then the minimum is reached at the critical point here. So here, what's the conclusion? Well, we have a global minimum at x equal 0.74, but there's no global maximum because it's reached at limit. All right, so let's do this again for the second interval. Now we're going to look at the interval 0, 2. So at 0, 2, what do we have? So again, we have the same open endpoint, so the same limit, so we can just reuse it here. So as x approaches 0 plus, we know that this is going to 1. Then the next point is at 0.74. So again, here at 0.74, this is going to give me, the function is going to give me 0.26. And now the new value is at 2. So if you replace x by 2 in the function, you're going to get 1. Aha! Now if you are looking for maximums, there's 2 of them. There's a max here reached by a limit, but there's also one here reached at a closed open endpoint, and the smallest possible value is still reached at the critical point here. So what's the conclusion? So we still have a global minimum at x equal 0.74. What about the global maximum? So this one, you have to be careful. Yes, one of them is reached by a limit, but then you just don't consider it. So this one has a global max, and it's at x equal 2. So here you have to consider the closed endpoint winning, okay, one of the biggest value. And now for the last interval, so between 0 to infinity. So again, here 0 is the limit that we had earlier. So my limit as x approaches 0 from the right, but now we have a brand new limit. Let's do it in darker green. So going to infinity. So again, here, I'll let you do it as an exercise. It's not that difficult here. Okay, so this one, you can do it just by doing a direct evaluation to infinity. So you can double check that this limit goes to infinity when x goes to infinity. So how do you set up your table with these 2 open endpoints? So the first one, so it's the same thing here, x approaches 0 plus. And then we know this is giving me 1. Then our critical point, 0.74, still giving me 0.26. And now our brand new limit, going to infinity, is giving us infinity. So when you're looking for a biggest value here, of course, nothing beats infinity. So we have a maximum. And for the lowest possible value, well, we still have that good old critical point to count on. So here we have a min right here. So for the conclusion, so same thing, we have a global min at x equals 0.74, and there's no global maximum. So no global maximum. Again, this is 3 questions in one. Okay, so I don't want you to freak out with these 3 examples. Not normally in a question, it's one function with one interval, and you just have to do, the limits corresponding to the open endpoints, and then just make the correct conclusion. But for that section, that's it. That's all. Bye-bye.